July 7th, 2026. Today, we are living in the shadow of a book that was published exactly 339 years ago on this very day, and that changed the course of human history forever. It is a book that weighs about 2 kilograms, contains roughly 500 pages of dense Latin prose, and is filled with geometric diagrams that look impossibly complex to the untrained eye. But within those pages lies the key that unlocked the universe. It is Isaac Newton's Philosophiæ Naturalis Principia Mathematica, the mathematical principles of natural philosophy. And today, on July 5, 1687, the Royal Society of London published this work, effectively ending the medieval view of the cosmos and laying the groundwork for the Age of Enlightenment. It was the moment when humanity stopped guessing about the heavens and started calculating them. Now, let me tell you why this matters, not just as a historical curiosity, but as a living, breathing lesson in how science works. Because the Principia is not just a book. It is a monument to the power of human curiosity, the power of asking the right questions, and the power of refusing to accept easy answers. It is the story of a man who, driven by an almost pathological obsession with understanding the universe, single-handedly created the framework that would dominate physics for the next 2 centuries. And it is a story that Richard Feynman, the patron saint of this channel, would have absolutely loved. Let me set the stage for you. The year is 1687. The world is still struggling to recover from the devastation of the 30 Years' War. The scientific revolution is in full swing, but it is a chaotic, contentious affair. Galileo has been dead for 45 years, but his ideas are still considered heretical by the Catholic Church. Kepler has shown that the planets move in elliptical orbits, but he could not explain why. Descartes has proposed a theory of vortices, swirling cosmic fluids that supposedly carry the planets around the sun, but it is vague and unmathematical. And then there is Newton, a Cambridge professor, a man who is famously reclusive, famously difficult, and famously brilliant. He has been working on the problem of gravity for nearly 2 decades. The story goes that he saw an apple fall from a tree in his garden at Woolsthorpe Manor, and that inspired him to think about the force that pulls the apple down. But that story, as charming as it is almost certainly apocryphal. Newton himself told the story to his biographer, but it was likely a simplification, a way of making a complex idea accessible to a general audience. The truth is far more complicated. Newton had been thinking about gravity since at least 1665, when he was a student at Cambridge and the university was closed due to the plague. He had retreated to his family home in Woolsthorpe, and there, in isolation, he had begun to formulate the ideas that would eventually become the Principia. He had calculated the force needed to keep the moon in its orbit around the Earth, and he had compared it to the force of gravity at the Earth's surface. He found that they matched to within a few percent, but he was not satisfied. He needed more data, more precise measurements, and it would take him another 20 years to get them. The Principia is divided into 3 books. The first book deals with the motion of bodies in general, laying out the famous 3 laws of motion: the law of inertia, the law of acceleration, and the law of action and reaction. The second book deals with the motion of bodies in resisting media, such as fluids and gases. And the third book, the most famous, deals with the system of the world, applying the laws of motion to the motions of the planets, the moon, and the comets. It is in this third book that Newton presents his law of universal gravitation, that every particle of matter in the universe attracts every other particle with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between them. This was the key that unlocked the heavens. With this single law, Newton could explain everything: the orbits of the planets, the tides of the oceans, the precession of the equinoxes, the paths of comets. It was a unification of the celestial and the terrestrial, a demonstration that the same laws that govern the fall of an apple also govern the motion of the moon. It was a radical departure from the Aristotelian view that the heavens were perfect and unchanging, and that the earth was the center of the universe. Newton had shown that the universe is a single coherent system, governed by a single set of laws. And he had done it with mathematics. Now you might be thinking, this is all very impressive, but what does it have to do with me? The answer is everything, because the Principia is not just a historical artifact, it is the foundation upon which all of modern physics is built. Every rocket launch, every satellite orbit, every GPS navigation system, every prediction of the motion of an asteroid, every calculation of the trajectory of a spacecraft to Mars, all of it is based on Newton's laws. His equations are so accurate that they are still used today, for almost all practical purposes. It is only when you get to extreme conditions, when you are dealing with objects moving at close to the speed of light or in intense gravitational fields, that you need to replace Newton's laws with Einstein's theory of general relativity. But for the vast majority of problems, Newton's laws are more than sufficient. They are the language in which we describe the universe. But here is where the story gets really interesting. Because the Principia was not just a scientific triumph, it was also a deeply personal struggle. Newton was a man of immense intellectual power, but he was also paranoid, secretive, and deeply religious. He believed that his discoveries were divinely inspired, that he was revealing the mind of God. He was terrified of criticism, and he often delayed publishing his work for years, sometimes decades, because he was afraid of the controversy it would generate. The Principia itself was only published because of the intervention of Edmond Halley, the astronomer who would later predict the return of the comet that bears his name. Halley visited Newton in 1684 and asked him what he thought the orbit of a planet would be under an inverse square law of gravity. Newton replied, without hesitation, that it would be an ellipse. Halley was astonished. "How do you know?" he asked. "I have calculated it," Newton replied. Halley urged Newton to publish his calculations, and Newton reluctantly agreed. Halley then personally financed the publication because the Royal Society had run out of money after publishing a book on the history of fish. This is a beautiful detail because it reminds us that science is not just about brilliant ideas. It is about patronage, about politics, about the messy human reality of getting things done. Halley's support was crucial, and without it, the Principia might never have seen the light of day. The impact of the Principia was immediate and profound. It established Newton as the preeminent scientist of his age. It transformed physics from a speculative philosophy into a rigorous mathematical science, and it inspired generations of scientists to come, including Albert Einstein, who once said that Newton's work was the greatest intellectual achievement of mankind. Feynman, for his part, held Newton in the highest regard. He saw Newton as a kindred spirit, a man who was driven by an insatiable curiosity, a man who was not afraid to challenge the established wisdom, a man who was willing to do the hard work of calculation to uncover the truth. Feynman often quoted Newton's famous line, "I do not know what I may appear to the world, but to myself I seem to have been only like a boy playing on the seashore, and diverting myself in now and then finding a smoother pebble or a prettier shell than ordinary, whilst the great ocean of truth lay all undiscovered before me." Feynman loved that quote because it captured the humility and the wonder that he believed were essential to the scientific enterprise. Newton, despite his towering intellect, never forgot that there was always more to learn, always more to discover. And that is the lesson I want to leave you with today. On this day, July 5th, 2026, as we commemorate the 339th anniversary of the publication of the Principia, let us remember that the quest for knowledge is never finished. Newton gave us the laws of motion and gravity, but he did not answer every question. He did not know about quantum mechanics. He did not know about relativity. He did not know about dark matter or dark energy. Those mysteries were left for future generations to solve. And today, we are still solving them. We are still building on the foundation that Newton laid. We are still asking the questions that he would have asked. How does the universe work? What are the fundamental laws that govern it? What is our place within it? These are the questions that drive us, that motivate us, that give our lives meaning. They are the questions that Feynman asked and that he encouraged us to ask. They are the questions that make us human. But July 5th is not just about Newton. It is also the birthday of a man who continued Newton's work, who extended it into new domains, who helped to create the science of thermodynamics. His name is William John McQuorn Rankine, born on this day in 1820. Rankine was a Scottish engineer and physicist who, along with Rudolf Clausius and William Thomson, Lord Kelvin, developed the science of thermodynamics. He formulated the Rankine cycle, which is still used today in steam turbines and power plants. He developed methods to solve the force distribution in frame structures. He was one of the founders of the science of thermodynamics. And he was a pioneer in the study of waves, both sound waves and water waves. Rankine's work is less well known than Newton's, but it is no less important. He helped to lay the foundation for the Industrial Revolution, for the development of steam engines, for the generation of electricity. He was a man who understood that the laws of physics are not just abstract concepts. They are tools that can be used to build a better world. And July 5th is also the day, in 1951, that Dr. William Shockley announced the invention of the Junction transistor. The transistor is the fundamental building block of modern electronics. It is the device that makes computers, smartphones, and the Internet possible. Shockley, along with John Bardeen and Walter Brattain, had invented the point-contact transistor in 1947, but the junction transistor was a significant improvement. It was a three-layer sandwich of semiconductor material, with the outer layers having too many electrons and the middle layer having too few. This created a device that could amplify electrical signals and switch them on and off, the basic functions of digital logic. The transistor revolutionized technology, and it earned Shockley, Bardeen, and Brattain the 1956 Nobel Prize in Physics. It is a reminder that physics is not just about understanding the universe, it is also about changing the world. And there is more. Today, July 5, 2026, the Earth reaches its aphelion, the farthest point from the Sun in its annual orbit. At approximately 8:30 p.m., the distance between the Earth and the Sun will be about 152.1 million kilometers, about 5 million kilometers more than at perihelion in January. Now, you might think that this would make a difference to the weather, that we would be colder in July because we are farther from the Sun. But that is a common misconception. The true cause of the seasons is the tilt of the Earth's axis, which is about 23.5 degrees. In July, the northern hemisphere is tilted toward the Sun, so the Sun's rays strike more directly and the days are longer, leading to summer. The variation in distance from the Sun has only a minimal effect, about 3%. It is a beautiful example of how science can correct our intuitions, how it can show us that the world is not always what it seems. And tonight, if you look up at the sky, you will see another celestial treat. Mars and Uranus will be in close conjunction, with an angular distance of only about 6 arc-minutes. They will appear between the Pleiades and the Hyades, two of the most famous star clusters. Mars will be visible to the naked eye, but Uranus will require binoculars or a telescope. It is a reminder that the universe is always changing, always offering us new things to see, new mysteries to ponder. So let us bring all of these threads together. On July 5th, we have the publication of Newton's Principia, the birth of Rankine, the announcement of the Junction transistor, the Earth's aphelion, and a conjunction of Mars and Uranus. Each of these events is a testament to the power of human curiosity, to the relentless drive to understand the world around us. Each of them is a reminder that we are part of something vast and beautiful and infinitely surprising, and each of them, in its own way, embodies the spirit of Richard Feynman. Feynman would have loved all of this. He would have loved the sheer variety of it, the way that physics connects the motion of the planets to the operation of a transistor, the way that the same laws that govern the Earth's orbit also govern the behavior of electrons in a semiconductor. He would have appreciated the humility of Newton, the man who saw himself as a boy playing on the seashore. He would have appreciated the ingenuity of Rankine, the man who helped to create the science of thermodynamics. He would have appreciated the audacity of Shockley, the man who helped to create the digital age. And he would have appreciated the wonder of looking up at the sky and seeing Mars and Uranus in close conjunction, a reminder that the universe is still full of surprises. There is a story about Feynman that I have always loved. He was once asked by a student what he thought was the most important thing he had learned about the universe. Feynman thought for a moment, and then he said, "The world is so wonderful that I am lucky to be alive in it." That is the spirit that animates all of these discoveries, the spirit of wonder, of joy, of gratitude for the sheer fact of existence. It is the spirit that drove Newton to unlock the secrets of the heavens, that drove Rankine to understand the nature of heat, that drove Shockley to invent the transistor. It is the spirit that we can all share every time we look up at the night sky and see the stars, a reminder that we are part of something vast and beautiful and infinitely surprising. So tonight, go outside. Look at Mars. Look at the Pleiades. Look at the Hyades. Think about the fact that the Earth is at its farthest point from the Sun, yet we are still warm, still alive, still curious. Think about the fact that the laws of physics that govern the motion of Mars are the same laws that Newton discovered 339 years ago. Think about the fact that the transistor in your phone, the device that allows you to watch this video, is a direct descendant of the Junction transistor that Shockley announced on this day in 1951. Think about the fact that the science of thermodynamics, which Rankine helped to create, is what allows us to generate electricity, to power our homes, to run our industries. And think about the fact that all of this, all of human knowledge, all of human achievement, is built on a foundation of curiosity, of wonder, of the relentless drive to understand. That is the legacy of the Principia. That is the legacy of Newton. That is the legacy of Rankine. That is the legacy of Shockley. And that is the legacy that we, the curious ones, the ones who refuse to stop asking questions, are privileged to carry forward. Stay curious, my friends. The universe is speaking, and tonight it is speaking through a conjunction of planets, an aphelion, and the memory of a book that changed the world.